Good morning, everybody. It's a very snowy day, so I'm recording today's lecture because campus was closed and we don't want to get too far behind. We won't be bothering with the concept check today because there's really no need for me to take attendance since you folks will be watching this online. So let's get into thinking mode like we normally do. Now, we're used to seeing electrophilic carbon. We've been talking about it in the case of carbonyl compounds, and you learned a lot about it last semester. Typically with the alkyl halides, you did SN1, SN2, and these reactions are made possible because of the polarizability of carbon when it's attached to an electronegative element. Now we have a way of converting a alkyl halide into something called a Grignard reagent. And what happens when we do this, the carbon is now attached to a metal, and metals are very electropositive. Carbon is much more electronegative than almost all metals. It's kind of close in electronegativity to gold, but that's about it. So we get this reverse polarity. We now have a large partial negative charge on carbon, so it becomes nucleophilic. So I want you to think about that now. So we're reversing the typical reactivity we've seen. We've seen carbon acting as an electrophile, and now today, after a little introduction about some more reduction reactions, we're going to start talking about carbon as a nucleophile. And in order to make carbon nucleophilic, we have to get a partial negative charge on the carbon rather than what we have been seeing. Here's January 23rd concept check. Let's talk a little bit about that. We asked here what's the strongest electrophile and what's the weakest electrophile. The strongest electrophile is going to be the electrophile with the most positive charge on, in this particular case, on carbon. So positively charged things are usually, almost always, better electrophiles than something that's neutral. So in this series of compounds, the positively charged compound is going to be the strongest electrophile. We can draw a resonance structure which gets our electrophilic center right here on that carbonyl carbon. So the weakest electrophile now is going to be the one that has the smallest partial positive charge and maybe a little bit of steric hindrance. That's this one, because we have all of these electron donating alkyl groups very close to the electrophilic center. They're pushing electron density towards that electrophilic center and making it a little more stable. So it's not as good an electrophile as, for example, this aldehyde or even acetone, because we've added a few more electron donating groups. Now, in terms of nucleophilicity, this is a little bit new, but the same thing applies. Negatively charged compounds are going to be better nucleophiles than very structurally similar compounds that are not negatively charged. So in this case, we're going to start off the weakest nucleophile is the one that's neutral. We have lone pairs of electrons on this oxygen, and this thing can act as a nucleophile, but we would have to have a very reactive electrophile. So these compounds that are negatively charged, if we take a look at them, this particular compound, we have this negative charge, but we have a lot of electron withdrawing groups very close to that reactive center with the negative charge, and that withdraws some of the electron density and makes it a poorer nucleophile. Over here, we see this nucleophile negatively charged, so it would be a better nucleophile than this one, but this charge is delocalized between those two oxygens. And remember, whenever we can delocalize a charge, we stabilize that compound. And because we want this to be a nucleophile, if we stabilize it, we reduce it, there's not as much charge on the one oxygen atom. Over here, we just have an alkoxide type of negatively charged anion, so there's a lot of charge density on that oxygen. It can't be delocalized, so this is the strongest electrophile. I'm sorry, strongest nucleophile. Okay, so let's take a little sidebar. We're still talking about reductions here. You guys have saw last semester that you can use an amine to react with something like methyl iodide, and you methylate and make now a secondary amine. As it turns out, this amine is a slightly better nucleophile than this amine. So once we make our first product, it becomes more reactive than the starting nucleophile. And in fact, it's difficult to stop after one methylation, and we get two methylations. And then we'd have to do a separation. And as we make more and more of this, it starts out competing the original nucleophile so that we get this disubstitution. If we wanted this as our product, we have another alternative route. We can take formaldehyde in this instance and react it with a little tiny bit of acid with the primary amine. And remember, the first one of the intermediates that we get is this positively charged iminium cation. As it turns out, this is a very good electrophile, and it is easily reduced, and we can just put in a mild reducing reagent like sodium cyanoborohydride. This is a milder reducing reagent than sodium borohydride, and we'll talk about that in a minute, but it reduces this carbon hydrogen bond quite readily, and then we work it up with, and we end up getting our monoalkylated product so that we just have a secondary amine. So let's take a little bit, we call this whole process reductive amination because we make the amine by reducing an iminium, and we make the iminium by reacting it with a carbonyl compound. On the way to making the imine, but it never quite gets to the imine because this reduction occurs before we get to the full imine. So sodium cyanoborohydride is a very mild reducing reagent and will not reduce the starting aldehyde or ketone, because we can also use ketones. The reason is that there's this electron withdrawing group attached directly on the boron, so that's pulling some of the negative charge away, and that makes these compounds less hydride-like. They have a little bit less negative charge than just typical borohydride. This reaction's wide in scope. We can use aldehydes or ketones. We can also use ammonia. If we use ammonia, the iminium cation we would make does not have any alkyl groups on it. When we do the reduction, we just get a primary amine. If we use a primary amine on the iminium cation, there is an alkyl group attached to the nitrogen, and we get our secondary amine. We can even use secondary amines as our starting amine. They will react with the carbonyl compound. We know that the reaction pathway, barring having any reducing agent there, would lead us to an enamine, but in this instance the iminium ion gets reduced and we can form a tertiary amine. So this is a powerful reaction. I'm talking about it today because you're going to get a group assignment soon, and you may need to use this reaction. There may be other pathways, but this would provide an easy route to one of the problems you're going to have in your group assignment. So now we're going to talk about nucleophilic carbon adding to electrophilic carbon in the form of aldehydes and ketones. Okay, so here we see a reaction where we take HCN and we react it with, in this case, an aldehyde, and we see we form a carbon-carbon bond, and we also get our OH group. So we've converted our aldehyde into an alcohol, and we formed a new carbon-carbon bond right there. So let's take a look at this, how this reaction occurs. Notice we have a catalytic amount of KCN there. So as it turns out, HCN is a weak acid, and if we have a little bit of cyanide to start this reaction off, the cyanide will attack the electrophilic carbon of the aldehyde. We throw the charge up onto the oxygen atom, and we now have an alkoxide-like intermediate. It's alkoxide-like because we have that cyano group attached to it. But this is a decent enough base that it will pull the proton off of HCN, and that gives us our final product and reforms the cyanide so it can start the cycle again. This cyanide now can wander off and find another aldehyde or ketone, whatever the case may be. And we eventually get to through all of our reactants to get a high yield of this cyanohydrin. That's what we call this particular alcohol, because it has a cyano group attached to the same carbon as the OH group. Other forms of nucleophilic carbon, we take advantage of this fact that we can make carbon nucleophilic by attaching it to a metal. The most common sources that we will find right now in this course are alkyl lithium or organolithium compounds and organomagnesium compounds. The organomagnesium compounds, notice that the magnesium, because it's bivalent, still has one chlorine attached to it. It apparently seems like the magnesium just inserts itself into the carbon-chlorine bond, and when it does that, it gives us this reverse polarity to what we're used to, and the carbon atom is now nucleophilic. So metal-carbon bond in these instances, it is covalent, but it's very, very polar, and these things act like they're anions. Even though they have a lot of covalent character, they're very nucleophilic. Both organomagnesium compounds and organolithium compounds. So we're going to talk a little bit about some of the solvents that we need. These things are quite reactive. They're not very stable. And in order to get them stable enough so that we can then add our second reagent, which would be our electrophile, we have to do them in very polar, non-protic solvents that typically have an oxygen atom that can coordinate. We get this big complex that stabilizes this enough. It's still reactive, but it's stable enough that we can leave it in our flask for a little while and slowly add our other reagent, which is our electrophile, so that we're going to react it with this particular group. We have to, these organometallics are pretty strong bases as well. So we have to be careful. We can't have very active hydrogens. I already told you that we need aprotic solvents. That's because these things are quite strong bases and will just react with any kind of acidic hydrogen and destroy the reactivity of it as a nucleophile. So here we see an aryllithium compound. It will just abstract a proton and give us this compound as well as the hydroxide. Organomagnesium compounds will do the same thing. Very polar, and if we have any kind of acidic hydrogens around, it'll just rip that proton off and it quenches our organometallic compound. So we typically call these magnesium chloride compounds Grignard reactions or Grignard reagents after the person who invented them, Dr. Grignard. But they are strong bases, both alkyl lithium and Grignard reagents. So they're strong enough even to pull a proton off of a terminal alkyne. Terminal alkynes are a little bit more acidic than most hydrocarbons. Okay, alkenes are not nearly as acidic, and alkanes are even very much less acidic. Now, here's a convention alert. Organic chemists often talk about base strength using the pK of the conjugate acid. Remember, the weaker the conjugate acid, the stronger the base that formed that conjugate acid. So here we're talking about the fact that terminal alkynes have a pKa of about 25, and in this instance, the conjugate acid of this base is methane, and methane is very much not acidic. it has a pKa of around 50. Now remember, you're used to talking about pKa's in water, in which case they have to be somewhere between 0 and 14. When we get into organic solvents, we can have much stronger bases because there's no acid, weak acid like water around, and these are very weak acids, so that we can do these types of reactions in organic solvents. But in this instance, so the pKa for this alkyne is 25. The pKa for the conjugate acid of this base is 50. So this is a very strong base. And remember that the reaction always goes to give the weaker conjugate acid-base pair. And this reaction would go very much to completion. So let's take a look at the nucleophilic addition of a Grignard reagent to the carbonyl carbon. So here's our nucleophile. We have it red as always, and we have a very polar carbon-metal bond here that will act as our nucleophile, and it attacks the carbonyl carbon. We throw the negative charge up onto the oxygen, and the reaction just stops there. It coordinates with the magnesium and the chlorine. We get kind of a mess, but we work this up typically by adding a little bit of extraneous acid. It's a second step. So in this particular reaction, we let this go to completion, and then the chemist has to intervene and throw in a little bit of acid to get the reaction to go to completion. Then we work it up and get rid of all of these salts and everything. We usually take this up in some kind of organic solvent and purify our compound. We can get alcohols from aldehydes and ketones. Take a look at the mechanism, and this will help explain it. So remember, these are going to attack the carbonyl carbons of each of these, form a new carbon-carbon bond. If we use formaldehyde, we get a primary alcohol. If we use another type of aldehyde besides formaldehyde, we get a secondary alcohol. And if we use a ketone instead of an aldehyde, we now form a new carbon-carbon bond, that's this one, and we get a tertiary alcohol. So just be aware, this particular reaction, formaldehyde is a gas and at room temperature, and it's hard to use. So we typically use something called paraformaldehyde, which is a solid polymer of formaldehyde. It can be heated and depolymerized in situ, that is in the reaction mixture, to give gaseous formaldehyde, which is then, we can just bubble that through our Grignard solution and get a final product after workup. Okay, now here's a sign of things to come. We have yet to encounter esters, but esters have a carbonyl group. It's an electrophilic carbon. It's not as electrophilic as aldehydes and ketones, but when we have a strong nucleophile, like a Grignard reagent, it can react with that electrophilic carbon. And in the case of the Grignard reagent, adding to an ester, we get a tertiary alcohol. So why do we get a tertiary alcohol? Let's take a look at the mechanism for the reaction. So we get a nucleophilic attack at the carbonyl compound and forms this tetrahedral intermediate. What's different about this tetrahedral intermediate as compared to aldehydes and ketones is that we have these two oxygens atom attached to what was formerly the carbonyl compound, and this can actually leave, and we can push our arrows to show it leaving, and we'll be doing a lot of this in the next module when we talk about carboxylic acid derivatives, and that's what esters are. They're a derivative of carboxylic acid. So this group can leave, and when it leaves, we reform our carbon-oxygen double bond, and we have a ketone. As it turns out, these are more reactive towards the Grignard reagents than the starting esters, so they will just react and give us upon workup, our tertiary alcohol. So in the case of esters, we get our initial attack, we form a ketone, we can't isolate it because we have a very reactive nucleophile, and a more reactive electrophile than our starting electrophile. So it just gets another Grignard reagent added to it to form what is eventually the tertiary alcohol. So here's the three key reactions of Grignard reagents. With addition of Grignards to aldehydes gives us secondary alcohols, except for that one instance when we use formaldehyde and we can get a primary alcohol. Addition of Grignards to ketones gives us a tertiary alcohol. And with esters, we get two of our Grignard reagents attached to the carbonyl carbon, and we also get a tertiary alcohol. So that's our summary for the reactions of Grignards with carbonyl compounds right now. Take a look. Here's some specific examples. I won't go over them. You can take a look at them on the slides. We see specific examples in these two slides. We can use Grignard reagents for other things. We can insert magnesium into an aryl carbon-bromine bond to get an aryl Grignard reagent, good nucleophile. Remember, we talked about these things as being very good bases. Oftentimes in mechanistic studies, in biological studies, we want to replace a hydrogen with a deuterium. It gives us a little handle so we can watch what's going on in certain reactions or in biological pathways by having that deuterium there. Remember, deuterium is just an isotope of hydrogen, but it has a proton and a neutron in it, so it has twice the mass of a hydrogen atom. And if we can label things in specific places, we can use that deuterium to kind of figure out what's going on. So we often want to do this. There's no real value in these other than delineating mechanistic pathways in both reactions in the lab and in biological systems. Now, these Grignard reagents, as I mentioned, are quite good nucleophiles. We saw that they react with a less electrophilic thing like ester. They'll also react with carbon dioxide. Remember, draw the Lewis structure of carbon dioxide, and it looks like a carbonyl compound. In fact, it looks like a carbon with a carbonyl compound on each side, and that carbon is a little bit electrophilic, and we can attach our aryl group. We can form a bond between this carbon, and when we work it up, we will get the carboxylic acid. Grignard reagents will also react with epoxides. You learned about epoxides in Organic 1. Our nucleophilic carbon will attach to the very unstable carbon of our epoxide, because remember, there's a lot of ring strain here. It wants to break up. It's a two-step reaction too. So here we see a specific example of a Grignard reacting with a substituted epoxide. They're very strong electrophiles, and they will attack the least hindered position of the epoxide. So we'll get much more reaction here than over on this side. That opens up the ring, coordinates with the magnesium, and then we work it up under acidic conditions to get the final alcohol product. So the Grignard reagent's very versatile. We've just talked about a couple of things. This is a concept map of the reactivity of Grignard reagents and all of the different electrophiles that we can react it with. I don't know if you can hear that, but it's very windy out here right now. So I'm going to be shoveling snow later. One of the things I want to talk about, and this will be coming up in your group assignment that I'll be posting tomorrow, I want to talk about something called a retrosynthetic analysis. And this is really thinking backwards. We're used to seeing reagents, and we do reactions with those reagents to go forward to make products. Well, what if we wanted to make this? Retrosynthetic analysis says what we do is we take a look at what kind of chemicals we have in the lab or that we can buy. We can't buy this, then we have to figure out how we can make it. So we have to think backwards. So one of the ways of thinking backwards is saying, how can I make this from smaller pieces? I now know how to make carbon bonds, so I could think about, could I disconnect this in such a way that I have an anion and a cation. Well, we can't actually do this, although we can make this anion. This would be a very difficult cation to make. But if we could make these two things, they would just clip together and form a carbon-carbon bond. Now, this kind of arrow means we're going backwards. We're going from products to reactants that we think we can use to go in the forward direction. Okay? So if we could make this, we would be able to make this. So we say we need a nucleophilic piece and an electrophilic piece. Here's our nucleophilic carbon. This is an electrophilic carbon, so we can make this carbon react with this carbon because it's nucleophilic and form our carbon-carbon bond. So we thought about it. We came up with a way to make it. Now we do the reverse reaction. We take our aryl bromide, we react it with magnesium to get our nucleophilic aryl group. It will then attack the electrophilic portion of acetone and form the anion, which we then work up with some acid to form this. Now, one of the things I want you to think about when you start doing synthesis, you're going to have to reach back into some of the reactions you learned in 2513. So one of the things that you want to be aware of is you learned how you can make any one of these from the others. If I give you ethanol, you have the ability now to figure out how to make the aldehyde from ethanol. This is propanol. We can easily oxidize that to get the carboxylic acid. We can easily convert an alcohol to an alkyl halide, typically chlorine or bromine. That's an easy thing. And we can do an elimination reaction to get this alkene. So if we have any one of these, we can get to any one of the others. If you forget how, go ahead and do it. You don't need to give me the reagents here because you're going to do a larger synthesis, might be 3, 4, 5, 6 steps. And if you forget the particular reagents you need to go from one of these, that's okay. You won't lose a lot of marks, but you can do this into conversion. And I want you to put these probably on your cheat sheets, at least till you get used to it, to remember that you can make any one of these from any one of the others. You may have to go through one to get to the next one, but if you have one of these, you have a pathway to make any one of these. That's a very important thing to remember. Okay? So, restrictions on Grignard reagents. They're very reactive, and Grignard reagents cannot be prepared in the presence of any of these groups because it will compete with the electrophile you're trying to react it with. It'll pull off that proton of an alcohol, so you can't have any alcohols around. You can't have any amines. It'll pull off the proton of an amine if it's primary, secondary amine. It'll pull one of those protons off. It'll pull that proton off. These are much more acidic than the alkyl groups that are formed by pulling that proton off with a reagent. If you're trying to react another portion of the molecule, you can't have these things around as well because they're electrophilic. So you have to know about that. So let's see some examples of that. Let's do a retrosynthetic analysis on this reaction. Just like I just said, we could work backwards from here to here. We want to get to this compound, and can we do this? Let's think about it. Let's do a retrosynthetic analysis, and there's our retrosynthetic arrows, and we say, if I could make this Grignard, could it react with acetone, just like we did with that aryl compound, so we could make our Grignard from this alkyl bromide? What happens when we do that? Well, as soon as we throw this in, we throw our magnesium in, we see some stuff going on, we're happy, we add our acetone, and then we work it up, and we get this, okay? What happens is, as soon as you make this Grignard reagent, it's very reactive, it's just going to pull off that proton That's going to go around, pull off that proton, and we're going to get this when we get our workup. Because Grignards are incompatible with an OH group being there. Same thing would happen here. If we tried to make this Grignard reagent, it's just going to react with itself. So we can't make that. We're going to end up with this compound. Unless we want it, it's going to be, we can't use this thing as a nucleophile because there's a very reactive portion on the same molecule. So what we can do instead is protect it. Now we talked about our reactions of aldehydes and ketones with alcohols. One way to protect this is with an alcohol. In this particular instance, we could make the dimethyl acetal of this ketone. Then we can make this Grignard reagent because acetals are very comfortable in basic conditions. We can go ahead and make this compound. We can add an electrophile. We're going to attack from this carbon is going to attack this carbon, form our carbon-carbon bond, which we see here. And then when we do the acid workup, we're going to protonate that. And as long as we have some water, we can add some more water at the end. We will then deprotect our carbonyl group and get back to our normal condition, the compound we were looking for. So don't forget about protecting. You learned about how to protect OH groups in alcohols last semester. Now we have a way of protecting carbonyl groups. More often than not, we will use ethylene glycol. We talked about that earlier. Instead of making this kind of acetal, we would make a cyclic acetal, which are a little bit more stable than these types of acetals. So really, we would use ethylene glycol, not ethanol. Okay, so we can also use bases to pull off the protons of these terminal alkynes. We could pull this off with a Grignard reagent, or we could use another strong base like sodium amide. This NH2, it's called amide. That's negatively charged nitrogen. Remember, whenever we have sodium or potassium, it's going to have a positive charge. Whatever it's partnered with will have the negative charge. So this amide will pull off that proton and give us our acetylide anion. Okay, so this particular anion is a good nucleophile, and it can react with a carbon of something like acetone because it's electrophilic, and we form a carbon-carbon bond. We have the sodium salt, and we can just work it up with a mild acid. In this case, we're going to use ammonium chloride to protonate that oxygen and get our final product, and there's the carbon-carbon bond we formed. Another type of nucleophilic carbon comes in these compounds known as ylids. We're going to use this particular ylid, but an ylid is a compound that has a negatively charged carbon next to a positively charged heteroatom. Remember, when we have 4-coordinate nitrogen, it's going to have a positive charge. So this, we talk about this as being a ylid. This is also an ylid where we have positively charged sulfonium next to our negatively charged carbon. And we can also have positively charged phosphorus, phosphonium type of cation next to a negatively charged carbon atom. This is what we're going to use in something, this is known as a Wittig reagent after its inventor, Dr. Wittig. Okay, so if we take a look at this, and we often, organic chemists, you'll see organic chemists will draw this structure more often than they'll draw this structure. Inorganic chemists are more likely to draw this structure rather than this structure. These are just resonance structures. As it turns out, when we do high-level calculations, we find that this is probably a better Lewis structure because there is a lot of negative charge density on that carbon and quite a bit of positive charge density. That's what the blue is indicating on that phosphorus. But that then gives us this source of nucleophilic carbon. Okay, so let's take a look at what happens when we make a Wittig reagent, and then we'll talk about making a Wittig reagent in just a second. So once we have our Zwitter ionic species, I'm going to draw them this way most of the time. This thing is nucleophilic, and it will attack the electrophilic carbon. At the same time, it's possible that the oxygen atom can act as a nucleophile and attach to the phosphorus. And we get this cyclic intermediate, okay? This is called, and then it will just collapse. We see the movement of the electrons in the carbon-phosphorus bond reorganize to form a carbon-carbon double bond, and the electrons that are in the carbon-oxygen bond reorganize to form the phosphorus-oxygen double bond. This goes in high yield. The formation of the especially stable triphenylphosphine oxide byproduct drives the reaction to give the alkene product. This is the triphenylphosphine oxide. We have a strong phosphorus-oxygen bond. That is the enthalpic driver of this reaction, so it's thermodynamically favorable. Okay, so we prepare the Wittig reagent via using something like triphenylphosphine. We use this a lot because it's convenient for the workup. It's easy to separate out from everything. We can use other compounds, but this just happens to be a convenient reagent for workup after to get rid of the phosphorus oxide that forms. So this is a decent enough nucleophile that it can react with alkyl halides. We typically don't use secondary alkyl halides because elimination is typically favored, but we can get a high enough yield so that we can make this compound. We usually will use a primary alkyl halide if we can, if it works. We only use a secondary alkyl halide if we have to. We can get these positively charged phosphonium halides. And then we use a strong base, something like sodium hydride or sodium amide. Sometimes we could use a Grignard reagent, but this is not really acidic, so we need a strong base. We need a very strong base to pull off this proton to form our phosphorus ylide, which is our Wittig reagent. It's our source of nucleophilic carbon. So we can react, this reaction goes in high yield because the methyl triphenylphosphonium bromide is very easy. We have an SN2 reaction with a methyl halide that's going to go in high yield. Okay. Then our second reaction, we just use a base. In this instance, we're using an alkyl lithium as a base. It's a strong base, and it'll just pull off one of those protons on this carbon. These are slightly acidic because they're next to this positively charged phosphorus center, which makes it a little bit easier to pull off that proton to get our Wittig reagent. We can really only be done with primary and some secondary alkyl halides. Again, I want to reiterate that. So once we form our Wittig reagent, we form our oxaphosphatane intermediate, and then that just flies apart to give us our carbon-carbon double bond, and the driver of this reaction, the triphenylphosphine oxide. And when I talk about it as being the driver, I'm talking about thermodynamics. Here's the mechanism, and has an added step. And this step is, there's good evidence for this step. Normally, we might not think of this, but there's good evidence for this step. So we make our phosphonium salt. We use a base to make the ylide. The negatively charged carbon reacts with the electrophilic carbon of our carbonyl group, and we get this thing. It's called betaine. Okay, it's a zwitterionic species, and it actually closes to form the oxaphosphatane that we showed in our mechanism. And what happens is there's a lot of steric hindrance, and this is a minor product and this is a major product. So when they collapse, the Z-alkene is favored in the case of the Wittig reaction. We get more of the Z-alkene and only a little bit of the E-alkane. And it has to do with these intermediates. This intermediate is a little bit more favorable for steric reasons than this intermediate. And we end up with our Z-alkene as the major product. There's a derivative of the Wittig reaction. It's very much like it. It's called the Horner-Wadsworth-Emmons reaction. You will hear about this in your, I think this is question 5 in your individual assignment. So we have these phosphonate esters. This is a very electron withdrawing group. It withdraws enough electron density to make the protons on this carbon slightly acidic. We need a strong base again. In this instance, they're using sodium hydride. Sodium hydride will pull off one of those protons on that methylene group right there, and we get this anionic intermediate, and it's now a nucleophilic carbon, and we throw in an aldehyde to get an electrophilic carbon, and lo and behold, out pops an alkene at the end. Let's take a look at the mechanism. So once we make our phosphonate ester, we can pull off this proton to make this anion. It just attacks the electrophilic carbon, and we get this type of intermediate. It then does a ring closure to form this, and just like the Wittig reagent, that collapses to give us our alkene and this derivative of phosphoric acid. It's an ester of phosphoric acid anion. So here we see, this is from Roman Valulin. He has a lot of mechanisms up there. This goes through the mechanism in detail. We can pull off that proton. Again, what happens is this reaction is slow to get this cis-oxyphosphatane. If we take a look, it's because of steric hindrance. This is a high energy intermediate, but we can get this one, and notice now, it's hard to see, but our two groups like to be trans to each other, and in this particular instance, the E-alkene is favored. So if you want the Z-alkene, you would use a Wittig, and if you want the E-alkene, you would use the Horner-Wadsworth-Emmons olefination. We prepare the phosphonate ester from triethyl phosphite. This is proposed to go through an SN2-like intermediate. This will attack this, and then we get some rearrangements until we finally get our phosphonate ester as our starting material for the Horner-Wadsworth-Emmons reaction. Okay, so here's all the reactions that we've looked at in this chapter. Our little carbonyl group can undergo all of these reactions. Now there is one reaction here. We did not do reaction 15. We've looked at the rest of these reactions, okay? Notice that all of these start kind of the same. We get something that's nucleophilic and it reacts with the carbonyl carbon. So our first step is always our important step is always the nucleophile attacks the electrophilic carbon of the carbonyl group. If our carbonyl group isn't particularly reactive, or we have a poor nucleophile, we can soup this up by adding a little bit of acid. We can also add metal cations that coordinate it and make the carbon of the carbonyl group a better electrophile. So let's take a look now. We've done a few reactions. We've seen a few things. We've talked about some things. We have this compound and we want to make this. We did a retrosynthetic analysis and we thought we could use lithium aluminum hydride. Lithium aluminum hydride, we want to reduce this. Lithium aluminum hydride will reduce this to the alcohol. We saw that. The problem is it will also reduce this to the alcohol. So when we tried this reaction, we don't get the product we want. We get reduction occurring at both of them. If we try to use NABH4, NABH4 will only reduce this carbonyl. It's not strong enough to reduce an ester because esters are less reactive than aldehydes and ketones. So the sodium borohydride will just reduce this alcohol, and we want to reduce this to the alcohol. So how do we do this problem? Well, we're starting to learn. We haven't talked too much about esters yet, but esters are less reactive than aldehydes and ketones. Here we have ethylene glycol. We talked about the fact that we can use this to protect aldehydes and ketones. And if we're very careful and do this reaction with just one equivalent, we can protect only the carbonyl group of the ketone, and we leave the carbonyl group of the ester untouched. We can then react this with lithium aluminum hydride. Remember that these acetals, in this case a cyclic acetal, are stable under basic conditions. So we do this reduction, we work it up with a little bit of acid, and the acid protonates both the oxygen, which was coordinated to this aluminum, and it deprotects at the same time as long as we have a little bit of water around, and we get the compound that we wanted. So if we know our chemistry, we can even do reactions that appear to be difficult. We use protection strategies to protect the vulnerable groups and go ahead and react the group that we want to react. Okay, so next class we're going to start on the preparation of ketones. I'll get all of that ready for you, and that's it for today. Thank you.